Perspective from Greenland ice sheet. And to be honest with you, I can't think of a better person to give us this talk. To me, I've had an opportunity to work with her in the past on a project, and I don't know that there's somebody that knows Greenland better than Åsa in the back of her hand. Anyway, a little bit about Åsa. She earned her bachelor's degree and master's degree from the University of Copenhagen, and she earned her PhD from Princeton University. Dr. Rennermalm is a physical geographer who specializes in climate change and hydrology in the polar regions. She is currently studying how water is transported and retained within the Greenland ice sheet in order to better understand how much meltwater escapes to the ocean and increases global sea levels. Her work involves modeling, satellite, and in situ data analysis and fieldwork. She has participated in several field expeditions in the Arctic, mostly in Greenland. Take it away, Åsa.
Oh, cool.
All right, we're gonna have five.
Let's see if, does this mic work? Yeah? Yeah? Okay, awesome. All right, we're a little delayed because we're trying to get my slides to be connected, and oh, fantastic, here they are. I'm really happy about this. I mean, I was going to tell you some stories, but I have some pretty cool videos to show you. So I'm pleased that it's working. Let me just get situated over here.
Do you need a laser pointer?
I do not need a laser pointer. I don't like laser pointers.
Okay, just checking.
Let me just keep track of myself. I'm going to start with a little bit of a story. Is something? Yeah, there's caption over here if you can't understand what I'm saying. Anyway, I'm going to start with a story from my fieldwork, just to give you a flavor of what it can be like. And it's a story from my most, it's my second most recent expedition that took place in April, May last year. And when we went, me and a couple other people went to the Greenland ice sheet, and we were here. This is the place we were, and I'm going to tell you a story, what happened right here. We are stuck. Stuck. We've been on Greenland for 10 days, and we are stuck. It's me and 5 team members. We left we came here with a supply plane from the Air National Guard. They transport US scientists to Greenland, and we flew with them 10 days ago to a place on the ice sheet called Camp Raven. At Camp Raven, we got 5 snowmobiles, the ones you see here on the picture, and all our gear. We loaded it up on sleds, and we set off to our first camp about 70 kilometers away from Camp Raven, which is this place. And we are stuck. After a big snowstorm, none of our snowmobiles will start. None of them. So we can't move a meter. Only how we can walk. What's even more frustrating is that our most important scientific equipment, our ice core drill, the whole purpose for us being here, is not working either. I've been on the phone with the people that borrowed us that drill, and they don't understand what went wrong. We think perhaps it's the very cold temperatures. It's gone below minus 30 degrees, and that's both Celsius and Fahrenheit. This is perhaps the most ambitious, most important expedition I ever led, and now I'm just seeing like failure ahead of me, and I feel so like heavy and sad and disappointed. Like all these months of preparation, all this work to put together the team, and now we're here and we're just stuck. We can't go anywhere, and we can't collect any data. The days are beautiful. It's blue sky, and the ice crystals in the air is creating these like absolutely amazing spectacles of sun halos around the sun that is around the sun and around the sky, and it's just incredibly beautiful. And it's perfect for doing science, except we can't do any science, and our only way forward is to somehow get back to Camp Raven. because at Camp Raven, there will be planes coming in with some limited supplies that maybe we can solve this problem. The problem is that we cannot go to Camp Raven because our snow machines aren't working. So we spend our days playing cards, frisbee. Every day I'm in contact with our logistics operator in a town, like out on the tundra on Greenland. And every day we decide to try and start the snow machines and see if we can get something going. And that's kind of the way out there. One of our team members brought a book with Russian plays, and we're contemplating doing what Shackleton did like 100 years earlier when he got stuck in Antarctica, and in reenacting Russian plays. And I actually start reading up on it, but we fortunately never get that far. One day, I'm sitting in the tent, and Mike, our guy who takes care of the snowmobiles, he's outside trying to get this started. And then we hear it, the roar of a snowmobile engine starting. And we're all like, just electric, and just get up from our seats, like dart out of our mess tent, and we're all gathered around this one snowmobile that's running. The engine is running after several days of nothing. And we're so excited, but also we know we need 2 snowmobiles. We don't want to just leave on one snowmobile in case it just dies down. So Mike goes methodologically from snowmobile 1 to snowmobile 2. We have like extra batteries and jumper cables and what have you, everything that we can think of. And that one doesn't start. And he goes to the next one. And that one doesn't start. And then the 4th one starts. And we see a way out of here. Me, Mike, and one other guy, we quickly get our gear together and get on those 2 snowmobiles, and we start driving back to Camp Raven. It's a 2-hour drive on the snowmobiles, and it's torture. Are we gonna get there? And it's so like uncomfortable too. Like you think like the ice sheet would be this like smooth, even surface, but it's not. It's like bumpy, and you're kind of sitting on that snowmobile, and it's not a particularly nice drive. And I'm wearing like tons of clothes. I have like long underwear and puffy underwear, and I had these like giant bibs and parkas. I'm like this. On my hands, I'm wearing these gloves that people wear when they climb Mount Everest. And it's kind of hard to wrap your hand around the steering wheel of the snowmobiles, but somehow we make it, and we go forward. And in the middle of it all, we take a break, and it's so like nerve-wracking, because I'm like, are we even going to be able to start the snowmobiles again? But we kind of have to take a break, because otherwise they might overheat. They're a little complicated. They do start again, and we keep on driving and driving and driving, and suddenly I see it. At the end of the horizon, I see this giant dome rising up, this huge white dome. And as we get closer, it just gets bigger and bigger, and I can see this 6-story building that the dome is on top of, and I know we are about to get there. That waypoint is this unbelievable radar station put in there during the Cold War in the 50s and left by the US military in the late 80s. And it's still there. It's still there in the middle of the ice sheet. This unbelievable engineering feat, and it's our waypoint, and we see it. And when I see it, I know we're going to make it. We're going to make it to Camp Raven. And we do make it to Camp Raven. And from that point on, everything is going to turn around for this expedition. We are able to get supplies. We're able to somehow fix the snowmobiles. Nothing is easy on this expedition. Every piece of data is a challenge, but now, from that point on, we are getting data. So yeah, that's the story from my fieldwork, how hard it was to even just get to collecting data. but eventually we got there. So what I'm going to show you today, I'm going to give you a little bit of a background what's going on in the Arctic and in Greenland and with glaciers, and then I'm going to show you some of the data we collected in this type of expedition and talk about my other expeditions as well. Okay, but first, I just want you to think a little bit about glaciers. About, I don't know, 20,000 years ago, the glacier was right here, like here in the middle of New Jersey. And since then, it's been retreating. And I just think this perspective of thinking about glacier as a dynamic phenomena that's been expanding and retreating over time is quite interesting. And I found this graphic recently that I want to share with you. It's an engraving made in the late 1800s. This is a glacier in France, okay? This is a time when glacier posed another problem. You see how this glacier, it's like depicted as a monster. Yeah, it's like this monster coming down of the hill. It's like ready to like devour whatever's beneath her in the valley. You see like the tongue of the monster is like these rivers coming out. This is a depiction of a glacier as a destructor, like something that will like take your farmland and take your houses away. And that has been the experience at some point in the French Alps. I went online to look at what this glacier looked like now. I couldn't find the exact same viewpoint. I think probably I need to go there. But here we go. This is a photo taken in 2005. And you can see, of course, that you see a much closer look at this glacier, but you also see that it's way up in the valley. And this is from 2005. And here's another photo from 2015. So you can those two photos you can compare, and you can see this massive change. So what's happening now globally is that glaciers are losing mass. And Arctic in particular. So let me show you what's going on. I'm gonna show you this animation of global temperatures. This is an animation made by NASA. It will show you the temperature departures from the mean temperature as it was between 1950 and 1980. Okay, so everything here is in relation to that. When you see blue colors, those are temperatures that are colder than that period between 50 and 80. The red and yellow colors are areas where it's warmer, okay? And this little movie, based on real observations, will start in the late 1800s, around the time of that engraving, and it will go all the way till today. You'll see there's going to be a lot of variability, and there will be like some details of hot spots and cold spots. But what I want you to look at is the big pattern here. All right, so let's travel to time. Oops, that's not time travel. Here we go. All right. Is it going? There it goes. So you'll see it'll circle through. You see the years up in the corner there. And here we are in the beginning of the 1900s. You can see still blue colors pretty much everywhere, colder than normal. Now we're getting to the 20s, the 30s. We have a little bit of warm period here during the Second World War. And then it cools a little bit in the 50s. We're going to get into sort of the average period here. We're in the 60s, the 70s, and now we're getting close to modern day. Here we are in the 80s, 90s, and now you see change is happening. Now we're getting to the 2000s, and we reach today. And pretty much everywhere on Earth is warmer than this period between the 50s and 1980s. Pretty much everywhere, warmer than normal. And you can also see that the reddest colors are up in the northernmost hemisphere, right? This is the Arctic region, and there in the middle of it all, you have Greenland and the Greenland ice sheet, this giant block of ice in the middle of the North Atlantic, right there. This is due to emissions of carbon dioxide and other greenhouse gases that we as humans, as a society, is emitting. So what I'm going to talk about today is how Greenland is affected by these changes. And the reason we should care about it, perhaps the most important reason, is because of the impact that melting of Greenland has on global sea levels. So here's a little cartoon that I found. It's from the Union of Concerned Scientists. You'll see here, there's a man holding the hand of a kid, and the blue bar there, the blue line here at the bottom, is illustrating the observed change in sea levels since the late 1800s till today. So on average, that's how much sea level has risen. Okay, that doesn't seem like perhaps too much, but it's enough to cause problems. I mean, today, if you go to Miami, there'll be sunny day flooding is a result of rising sea levels, for example. But the big concern is the future. And here's another illustration that shows like the projections are very uncertain, which is why I'm studying the Greenland ice sheet. But here is some projections of the sea levels in 2050. So you can see that now sea level would reach here. Unfortunately for us here in New Jersey, sea levels might rise even more because of the impact on global currents and so on. And Greenland is one of the most important drivers of the present sea level rise and potentially also the future. So today, of the recent sea level rise, about 20 to 25% is coming from the Greenland ice sheet. And it's increasing. And I'm going to show you this picture. I'm sure many of you have seen it because we're in New Jersey. So this is from the Jersey Shore in the aftermath of Hurricane Sandy or Superstorm Sandy that caused so much damage in this state. And this storm happened during high tide. And that caused the storm surge to create so much more damage than it would otherwise. And what I want to propose to you is that this high tide, that is the sea level of the future. Okay? That's going to be our sea level in a couple of years. And so if you have more storms like this, we'll see more damages like this. So that's why we need to care about something so far away and remote as the Greenland ice sheet. And the Greenland ice sheet, my friends, are here in the middle, or quite far north, in the middle of the North Atlantic. It's the green area there. It's large. The ice sheet is large. I actually calculated how many times larger the ice sheet is than New Jersey. Probably most of you have an idea of New Jersey. It's 75 times as large as the area of New Jersey. If you take all the ice on the Greenland ice sheet and melt it and spread it out evenly over the world's ocean, I mean, that's not a scenario that's going to happen in any of our lifetimes, so don't worry. This is going to be pretty scary, but it's not going to happen in your lifetime. But it's just to illustrate how much water there is. If you melt out all that water, it will raise global sea levels with 24 feet. All right, to give you an idea what that is, I took this drawing, and I have to make it smaller, and then if you put 24 feet, it would be like this. These people have drowned now, for sure. It's gone. All right. All right, so let me tell you a little bit how this works. Okay, I want to give you some background information. So to understand Greenland's contribution to sea level, you also need to understand the controls of the mass of the Greenland ice sheet. And there are basically three processes. Okay, so the first process is, let's see, does it go? I have a little snowfall video here. No? Cannot play media. Okay, that's too bad. All right. Snow accumulation. Let's see I hope the next one goes because that one is way better. No. Oh, it is going, right? Okay. Another loss of mass is calving of icebergs. All right, this is a video caught by one of the largest outlet glaciers of Greenland. So here you see that process of icebergs being discharged from the ice sheet here, and here it's going out into the fjord. All right, that's a very important way that the ice sheet loses mass. Like these icebergs would melt and they will contribute fresh water to the global ocean, okay? And the third process that controls the mass of the Greenland is runoff. So let me play this one for you. Yes, great. All right, runoff is water, like meltwater runoff. This is a river. This is one of my study sites in Greenland. And here you see a little drone footage of this water. And here you see that water is coming from this little lake. And you see the background here. That's the Greenland ice sheet. So all this meltwater is coming from the ice sheet, like areas like this. Like this is melting and forms like ponds and lakes, and this water will flow into streams and rivers and eventually reach the global ocean. Okay, so we have these three processes: accumulation, ice discharge, and meltwater runoff. So snow is adding mass, ice discharge, and runoff is losing mass. My research, I focus on following the water, the meltwater of the Greenland ice sheet. Okay, what is super fantastic is that you can actually weigh the ice sheet from space. There are a pair of satellites called the GRACE satellites that can be used to weigh the mass of the ice sheet. And when you do that, I'm going to show you like a scientific graph now. You can see a dramatic change over time. Okay. This is data from that satellite. It started in 2002 and actually just stopped measuring, but there is a follow-up satellite, so we'll get new data. What you see here, you'll see two units on each side here, but what you see is changing mass on one side relative to the mass in 2006, and on the other side you will see how much sea level equivalent that is, okay? So all these red dots are observation of change. So one thing that you'll see in this graph is how it's like going up, like it's like zigzaggy. It zigzags. All right, that is actually a reflection of the accumulation, the increase in mass in the winter because of snowfall. And then it goes down during the summer when it melts and when icebergs are calving out into the ocean. But the most dramatic image here, right, the most dramatic take-home message from this figure is that it's going down. There is a loss of mass from the Greenland ice sheet, and that is why 20 to 25% of global sea level is coming from this part of the world. Okay, I'm going to show you a kind of a cartoon that I draw myself, and that's why it's not super awesome, but illustrative, I think. Okay, so if you think of the Greenland ice sheet as a dome of ice, and it's laying there on top of the tundra of Greenland, you can divide that ice sheet into two types of regions. Okay, and one is called the accumulation zone, and that covers the most of it, and covers the interior of the ice sheet, the high elevations. And on the fringes, the edges of the ice sheet, you have an area called the ablation zone. And that's where you have more melting and mass loss than snowfall. Because the glacier is moving, it will sort of, it's not going to like increase in size in the middle and disappear at the edges, because it also has an internal flow. But if you look at the surface, there's a net mass it's adding mass in the interior and losing in the exterior, or at the edges. My work is taking place at this transition zone, at the lower part of what we call the accumulation zone, and then the ablation zone, and I also work in the tundra. And to give some context to some things I'm going to talk about, I just want to explain a little bit about what the ice sheet is sort of, how it's kind of built up. Because you can think of the ice sheet as having three types of layers. You might think it's just ice, but there's more to it. Okay, so here I've kind of zoomed in on this transition region between the accumulation zone and the ablation zone. And you see I've kind of put like 3 layers in there. Those 3 layers are 3 types of water, frozen water. Snow, firn, and ice. All right, I bet everybody here knows about snow, right? Yes, and everybody knows about ice. But do you know about firn? It's my new thing, firn. Let me explain what firn is. Okay, snow. Let's start with snow. Okay, this is just a snowflake, right? And it has these beautiful crystals, and that's it falls on the top of the Greenland ice sheet, and it's going to be quite fluffy. You know, it could be compacted quite a bit if you have like lots of winds. You'll eventually have more snow falling on top of it, and more snow, and so on, and so on. So over time, like the snow will lose its fine structure. Like the crystals will be rounded off. It will become more compacted, like the air will become more compacted, less air, and it will continue to kind of lose its structure like this, and the air content less as well. And eventually, it'll become ice crystals, and the ice crystals now will enclose the air as bubbles in the ice, okay? So snow is has a lot of air in it. It's a porous material, and then ice, all the pores are closed off, like all the air are bubbles now. All right. And so firn is the medium in between. It's snow that has survived one melting season, and that eventually will become ice as more snow is laid on top of it and will compact it and so on. But what's kind of key here is that firn is a porous material. Water can infiltrate into firn. And let me explain why that matters. Okay, most of the melt that forms on the surface of the Greenland ice sheet runs off. Like here's a picture I took from a helicopter flying to one of our field sites. So you'll see like these blue rivers here. Like most of the meltwater will just flow into rivers like this and evacuate from the ice sheet. But quite a lot of that meltwater will actually melt at higher elevations in that accumulation zone. And here, because the firn and the snow are porous material, that meltwater may infiltrate into the snow and firn, and it can freeze into layers of ice. So what this woman is pointing out is a layer of ice within the firn. So I think it's kind of funny, like in my research, I look for ice in the ice sheet, which just seems kind of funny when you think about it. But now I told you about firn, so you can see how it can make sense to look for ice there. So that's what I do. And the reason I do that is because a few years ago, something pretty dramatic happened that changed our understanding of the Greenland ice sheet. And that was the year of 2012. I was there. I'm a witness. And I'm going to share that with you now. In July 2012, I was in Kangerlussuaq in southwest Greenland. I was in between field seasons. I had ended one field season and I was going to start another. And I spent my day in one of, you can see like a photo here of this town, Kangerlussuaq. It's a small town. It's actually a former US Army base. And so all these barracks are actually old US Army base quarters. And one of them are dedicated to scientists. So I was spending my days inside there trying to write my papers and stuff like that. And then people start coming up to me all of a sudden and be like, because they know I study water and I measure stream flow and things like that. And they were like, Åsa, you gotta go out and take a look at the river. There's so much water in the river. So I went down to the river and I was like, yes, there is a lot of water in the river. Yeah, I have never seen this river have so much water in it. And I've been to this place several years. First time was 2008. No, actually, first time was 95, that's right. But since 2008, I've been there every year. Okay, But you know, I study melting of ice sheet and rivers, so I kind of know that, you know what, it's going to melt during the day, but during the night, melting will stop, the water will fall. Except it didn't. The next day, the water level was higher. And the next day, it was higher. And now we had kind of a problem. The bridge across the river was about to flood over. So the county found like all their heavy machinery and tried to fortify this bridge. At this point, the whole town is standing down by the river and watching the spectacle of trying to save this bridge. And rumors are circulating that the pipe that brings fresh water to the village, which goes across this river, has broken, and that we have no more fresh water. And that, of course, is a problem because we need to drink water and so on. And so all kinds of things are going on there. And these people work really hard, but it does not help. Eventually, this bridge is just wiped out of these enormous water masses. This bridge was built, I think, in the 50s, so all this time it stood there, but now only the concrete structures are left behind. So here's another picture. So tremendous power in this water. All right, so why am I telling you this? This is a town with 400 people. It's not a town of global significance. It's important in Greenland. It's where the international airport is, but it's not a big place in Earth. I mean, if this happened in New York City, you know, everybody would know. But what I witnessed here was something going on at an enormous scale. And to give you an idea of that, I need to once again go back to satellite imagery. There are satellites that can actually measure if you have water on the ice sheet or not. Okay, and so with those satellites, we can create maps of which part of the surface of the ice sheet is melting and which one aren't. So here's the situation a couple of days before this bridge was wiped out. This is July 8th, 2012. So you'll see three colors here. The grayish colors are the tundra, and then the ice sheet is represented in two colors. You'll see red colors and white colors. So the white colors are everywhere on the ice sheet where you just have snow and ice that's not melting. But the red colors are the areas where there is surface melt. And so this situation right here is a situation of large but not like extraordinary surface melting of the Greenland ice sheet. You'll see how it's melting all around the periphery of the ice sheet, and it's melting in the southern part of the ice sheet. 4 days later, when that bridge was wiped out, when the water rose to the highest that I've ever seen, it looked like this. The entire ice sheet is melting on the surface. Now, people have gone to the highest point of the Greenland ice sheet and retrieved ice cores. And if you look into those ice cores, you can figure out when something like this could have happened before. So the previous time something like this is likely to have happened is in the late 1800s. Before that, we have to go all the way back to the medieval warm period. That is 1,000 years ago. That's when people from my part of the world, Sweden, Scandinavia, came to Greenland. That's when the Vikings came to Greenland. That's how long time ago something like this happened before. So a quite extraordinary event, right? And it changed things. I'm going to show you another satellite image. This is a satellite. It's a piece of a satellite image of a part of southwest Greenland made by a colleague of mine from his PhD thesis. Here you see a red dot labeled with a star. That's actually the site where I was stuck. And below it, you'll see these like bluish colors, right? Those are surface melting. You'll see how it forms like these kind of stream networks and ponds. And that's what you see here. And the reason I'm showing this is because this is very surprising. Like, we have not seen runoff up here before. Like, the reason we go to this place is because we think it will not have surface streams and so on. But in 2012, when you had that massive amount of melting, meltwater flowed on the surface all the way up here, which is quite far up on the ice sheet. And the reason we think that it was flowing on the surface, one possible explanation to that is that after 2012, we found extremely thick layers of ice in the firn. So below the surface, if you go down below the surface, if you drill a core and pull it up, which people have done, which I have done, at this place you found like meters thick ice layers. So the hypothesis is that these very thick ice lenses, these layers of ice, prevent meltwater from percolating down into the firn, which was what it did previously, and instead it flows off on the surface to the ocean, where it will increase global sea levels. So my research, I'm following the water on the Greenland ice sheet to understand how much of the water that melts on the surface makes it all the way to the ocean. And I start here. Where for as long as we know, water has actually percolated down into the firn and refrozen instead of flowing to runoff. So now I'm going to share with you some of my field data. So following the water. My study area is here in southwest Greenland. And here is a detailed map of some of the data I'm going to show you. This is from an expedition in 2017 where we didn't have any problems except, the team, but that's a different story. Anyway, we went to 5 places. There are different elevations. Here, this is the tundra right here in sort of dark colors, and then the white colors are the ice sheet, and all these lines are different elevations. So the elevation is increasing in that direction, and you can they're indicated here with meters. So we had like 5 sites at different elevations, and at each of those sites we retrieved about 20 meters of what we call firn cores. Because they're not quite iced yet. And so this is the setup. This is the team. This is the setup. All right, so the guys in the dark jackets and that rod sticking up, that is the ice core. It's not that complicated equipment, and yet complicated. So with that equipment, you can pull out like these chunks of cores. And then you see the guy in the orange jacket. He is analyzing those pieces of cores, and we like write down all kinds of information. Here's a close-up of a core, and it's about 70 centimeters long. So that piece is like this. And what we do is like we measure pieces of it. We measure the circumference, and we weigh it so we can calculate the density, like the mass of the ice and firn. And we also look at the stratigraphy, like how much, at what depth do you have firn, where is an ice layer, and so on. So we like record layers of ice in those cores, and then we go from the surface all the way down to about 20 meters. And let me show you what the data looks like. So here's like a photo of a piece of a core, and already here I think perhaps you can see how it's the sort of the medium change. Like down here you have like a piece of ice, for example, and then there's firn here. If you hold it up against the sun, it's really clear what's ice versus firn. All right, but the data we collected looks like this. In this figure. This is our site that is the highest elevation. And the black line is showing how density is varying from the surface down to 20 meters. So you can see that the density increases because it's being compacted by snow falling every winter, kind of pushing everything down, compacting everything. Okay? But you see how it's kind of a wiggly kind of line, right? There's a couple of places where you have a very high density. Okay? And so if I overlay wherever we have ice lenses, you'll see that often that correspond to each other. So all these blue lines here are observations of ice lenses and ice layers. So this is at the highest elevation, and we found, some ice, but not too crazy. And then if you go down to a lower elevation, you'll see that the density increases, and the amount of ice layers increases. And then you keep on going down in elevation, and you'll just, until we reach the lowest spot, and you can see how the amount of ice is just, you get more and more ice. So at the lowest spot, you have quite thick layers of ice near the surface. This is what we expect because you'll have more melting at lower elevations. But it was pretty massive ice layers there at the lowest elevation. So we think that perhaps if we have some big melt years in Greenland, those layers, if they become thicker, they could potentially prevent meltwater infiltration, as was happening at that Kangerlussuaq site, like a little bit lower down than this. The coolest thing about this data or this project is that my team was not the first team to be at some of these locations. Other people were there before us. And they didn't come there to study meltwater. They came to study snow accumulation. But they collected data that we find extremely useful. So I'm going to share with you some data collected by 2 expeditions at 2 of our sites. One about 30 years ago and one about 20 years ago. First is the Kameda expedition, a Japanese expedition, and then the Parka expedition, a US-led expedition at another site. They collected the same type of data that we do. And what I'm going to show you now is a comparison of the core that we collected in 2017 with the cores that they collected, all right? And if everything else had been equal, you would expect those cores to kind of look the same. So let me show you what it looks like. So let me start with the core from the Japanese team. This is our core that I already showed you. Now let's see what their core looks like. It's very, very different. You'll see that there's a lot fewer ice layers here. And the density is lower. And the same pattern is repeated at this other site. Here's our core, and here is the core that was taken about 20 years earlier. A lot less ice. So what I'm showing you here is evidence, like observational evidence of an increase of meltwater infiltration and refreezing in the Greenland ice sheet over this time period. So this supports, because the kind of evidence we have from that gray satellite, which only shows us what's going on since 2002, but you put that together, like this kind of observational evidence, together with what we see from the satellites, together with what we can learn from models, which also predict a rapid increase in melting right around this time, actually. This is when it started, in the mid-90s. That's when the big melting starts in Greenland. And so what we see in these cores supports all the other pieces of evidence. So massive change. All right, my research continues at lower elevations. So here are the 5 sites from 2017, and this is where we study taking cores from the dig into the ice or the firn and look what's going on. But I have sites at lower elevations, like pointing out with these red arrows here, where we look at this other process of meltwater flowing on the surface of the ice sheet, okay? And let me show you a quite nice video from one of my field sites. I had a very good fortune of being accompanied to our field site by a Pulitzer Prize winning photographer from the New York Times, and he shot this video. What you're looking at here is a stream on the surface of the Greenland ice sheet where we measured the amount of water flowing here. And this stream, it ends up in a moorland that takes this water into the interior of the ice sheet, where it will flow in channels inside and underneath the ice sheet, and eventually it will reach the edge of the ice sheet and flow out into the ocean. So there you see part of my team there. We put a rope across this river and measured the amount of water that flows in it. And the reason we do that is to compare with models, all right? We will never, ever be able to go to every river like this on the surface of the Greenland ice sheet and measure to kind of figure out how much water is flowing on the surface. But what we want to do with this kind of work is understand how do we model this and how good are our models. And this kind of work is still very much at the beginning. And so far, what we found out in the research I've done is a little bit conflicting, because at this place, we found that the models were very different from the observations. But I also have data from further down on the ice sheet where we have a longer record that covers like this. Here we stayed like about a week. We measured discharge around the clock, every hour, on the hour. Oh, that was hard. But further down, we also done these observations, and there we see like a good fit between the model and the observations. So what we're working on right now is to understand like why do we see this difference? And we think that some of the answer is beneath us, is below us. Like literally, if you stand on the ice sheet of Greenland and in this area and you look down, you won't see like a flat, homogeneous surface. You'll see this perforated surface. You're standing on a water landscape. And here's a photo I took looking down like this. So you see like all these little holes here. Those are what we call cryoconite holes, and they're full of water. And they have all kinds of sizes. This one is about 10 centimeters across. This one has a little sensor in it because we're trying to understand like how much water how is the water changing here. So what we notice is that this water storage here can actually store quite a large amount of water, and the depth of it seems to vary from year to year and over the season. So we're trying to figure out like how this kind of storage medium is delaying the flow into the rivers, and perhaps can explain some of the differences we see between our sites. Finally, I study the final step is measuring how much water flows off the ice sheet and reaches the ocean. So I have stations at the edge of the ice sheet in rivers on the tundra that drains the ice sheet. And here we're measuring how much water flows in these streams to understand like how much makes it out. And at our particular location, which is very close to the ice sheet, we've done measurements for over 10 years now. And we don't see a big change actually, which is, I was a little bit surprised by that. But it becomes really interesting when you compare the data that we've collected with data that collected by some colleagues of mine, which is further downstreams in this river, where the river is collecting water from a much larger area of the ice sheet. And they do see an increasing trend. They do see more water coming off the ice sheet in the last 10 years. So when you compare those pieces of data, what you have to conclude is that that water is coming from higher elevations, like the kind of places that I went in April, May, where that are so sensitive to how much melting occurs that sometimes the melting will flow off the surface and sometimes it infiltrates into the firn. So that was a bit of an overview of Greenland and what I do, and I guess I'll just leave you with some take-home points, and that is that Greenland ice sheet is a major contribution to global sea level rise. The main increase, it's increased a lot since the mid-90s, and the main increase is coming from ice sheet melting and runoff. But not all of the water makes it to the ocean. About 45% will infiltrate into the firn and refreeze as those ice layers. What we can see is that those ice layers are getting thicker. What we don't know is how that is going to affect the potential for meltwater to continue to infiltrate, or if it will, as was seen in 2012, it will flow off the surface. And then if we go to the lower locations and look at stream flow on the surface of the ice sheet, we're trying to understand how good our models are, because our models are the key to understand how Greenland is going to respond to future climate changes and what kind of continued sea level rise we might expect. And we found lots of interesting thing here, and that the surface layer that contains water, we call it the weathering crust, is perhaps one of those mechanisms that we need to study more to understand how water is stored and delayed on the very surface. And then finally, looking at the rivers on the tundra, we see more flow coming from higher elevations. And here, there's also a lot of evidence of delayed flow. All right, I'm just gonna, almost done, but I just wanna acknowledge how this kind of work could not be done without funding from agencies like NASA and the National Science Foundation. Absolutely critical. It could not be done without a big team of scientific collaborators from universities across the United States and beyond. And it could not be done without having a fantastic team. This is my Rutgers team that works with me to study the Greenland ice sheet. And I'm going to just end by singling out one of my collaborators, Karen Rogers. She is an undergraduate student at the Mason Gross program. She's an artist, and she joined our expedition in April, May, and she made a little movie that I'm going to show you now. And I just hope that it has sound. Let's see. Let's see. Does it have sound? All right. Oh yeah, we're going to get to sound. I hope we have sound, because she not only collected the video that you're going to see, she wrote the poem and she wrote the music. So, and the music is really nice. So let's see. We're getting sound now.
It's plugged in, so.
Let's see. Otherwise, you'll just see images. I guess not. All right, this is what it looks like. This is our field site. I'm sorry the sound isn't there. It really is fantastic. Maybe I can.
We can post it.
Wonder if I pull this out. No, it doesn't work. Oh, here we go. All right.
Hidden deep beneath us all.
Maybe it's like so.
Years and
I wonder if I can just get it onto the big one. All right. I'll do this like this, and let's see. You can hear a little bit, right?
relished in pleasing dreams. A bond beyond shared human experience. Longing to be heard. A transcendental sort of cold. Of a life once thought not worth living. a sudden urgency and hunger for only that, to live as vividly and wildly as ever imagined, hidden deep beneath us all. Years and years of unknown, experience and hurt, melt and growth. New snow will fall, and they will someday long to listen, just as long as you unearth the pieces of you, deeply rooted within craters and crevasses. Koyanak. Thank you.
All right, so with that, I'll end with this photo and me and the Dai 2 station. Thank you very much for your patience. All right, if anyone has questions. Yes.
I've been watching the Arctic ice sheet for many, many years, going way, way back.
Okay.
And you mentioned 2012, and that's one of the critical points in that whole scenario.
Right.
It was coming up to that point that the ice sheet was really disappearing. It also came out that all the people who had the models of how this thing's going to transpire, they found out they were all wrong. What they missed was when the ice sheet starts melting,
I think you're talking about the sea ice.
the light
Yeah.
starts shining through
Yeah.
and it heats it up even faster.
Mm-hmm.
Now, since then, it's reversed, and that's because what happened with the sun is it went into a low sunspot period, which does not warm the Earth up, and the ice started accumulating again, but not near as thick as what it was like beforehand.
Okay.
So I'm looking at this as coming into affecting the Greenland ice sheet and why we see so much warmth in the last couple of years in the northern hemisphere. It's because when the ice melts, more is exposed,
Right.
and everything just heats up.
Yeah. So what he's talking about is I think actually it's the example is like the Arctic sea ice, the cover of sea ice on the Arctic, which is also this absolutely amazing indicator of change. I think perhaps one of the most like these signals that our climate system is really changing is the dramatic loss of Arctic sea ice. And one of the reasons is that once that sea ice is kind of a thin layer of ice floating on top of the ocean. And when that ice disappears, it reveals a darker ocean. And all my students who take my course in Earth systems, they know, like if you have a dark surface, it will absorb more solar radiation and heat up faster. And so that it creates this feedback effect. So that's definitely in play. It's also happening in some ways over the Greenland ice sheet because the surface is getting darker. I mean, the ice sheet is so much thicker than the sea ice. Like the sea ice is like a meter, perhaps, like the thickest are a couple of meters. But the ice sheet at the thickest point is 3 kilometers. All right, Missy, yeah.
I was going to ask you about your firn research, your firn ice research. Have you been able to quantify the amount of meltwater that's actually been trapped as firn ice at this point to account for all of the melt that we're seeing on the surface?
Right. Yeah, so the question is, have we been able to account in our firn cores, like the amount of melt that has accumulated? That's something we're working on. I mean, I did some preliminary work that seems to match up with the observations, the model estimates. But it's definitely one of the interesting things with this kind of data. We can use it to actually try and quantify like how much meltwater is stored is as ice, and especially when you compare to these old cores, you can kind of quantify the change. So, I mean, there's definitely a lot more. Yes, in the back.
Why do we see disproportionately more global warming in the northern hemisphere rather than?
Yeah, I mean, one of the reasons is that you have like up in the Arctic, you have this like cover of ice and snow, and then when it's so sensitive to whether or not you are at freezing or not. So if you just you see it here all the time, like when you have snow and then it melts so quickly. It's like you just need to get over freezing And then you have this feedback effect of extra warming. Right, what, yeah. Okay, all right, green.
Has anyone looked at the land level change in Greenland as the ice sheet melts?
Absolutely. The question is, has anybody looked at the land level, like the elevation change of land as Greenland is melting? Yes. And guess what? It's rising up. Yeah, totally. It's one of another piece of evidence. All right, last question. All right. Yes.
Is there any correlation between geothermal activities such as like volcanoes and the amount of runoff?
Is there any correlation between volcanic activity and the amount of runoff? I mean, you do see, like, for example, the effect of Mount Pinatubo with a 92. You see like a drop in the amount of melting. So there is, like, because it had a global influence on it also influenced the Greenland ice sheet. But the driver for these changes, I mean, it is our emissions of carbon dioxide into the atmosphere. So let's stop it. Okay, great. Thank you very much.